everybody. I'd like to welcome you back to another Brown Bag webinar with us. And today we're so very lucky to have Dwarak Ravikumar with us, who's coming to us from outside of Phoenix in Arizona. Dwarak is a scientist at the National Renewable Energy Laboratory. His research focuses on evaluating and improving the environmental and economic performance of emerging circular economy technologies for CO2 and renewable energy systems, advancing methods in LCA to better evaluate emerging technologies, and using multi-criteria analysis, decision analysis to integrate LCA and techno-economic assessment. Prior to joining the NREL, Dwarak completed a 2-year research fellowship at the University of Michigan on developing LCA standards and improving the sustainability of carbon capture and utilization, or CCU, technologies. Dwarak has a PhD in civil, environmental, and sustainable engineering from Arizona State University. So welcome, Dwarak, and as usual, we'll take all your questions at the end if you'll send the questions to me, Holly Harris, privately via the chat. So welcome, Dwarak.
Thanks a lot, Holly. So before I start off my talk, I'd really like to thank EarthShift Global for sponsoring this talk and organizing and publicizing this talk. Thank you so much. And I'd like to also thank each of the audience members for taking time off their schedule to attend this talk. So thanks a lot. Just to give a brief introduction, I'm currently working as a scientist at NREL, as Holly just mentioned, and I've been conducting this research over the last 2 years. So I'm going to crisply summarize it over 30 minutes, hopefully, and I don't extend beyond that. So in today's talk, I'm going to talk about how we can apply this method of LCA that I call Anticipatory LCA, which was developed with part of a larger group, how we can apply it in the early stages of technology development, specifically carbon capture and utilization technologies, and improve sustainability outcomes in the early stages or in the low TRL stages. So that's the focus of today's talk. So before I start the talk, I'd like to acknowledge certain institutions and groups that have been very instrumental in this research. NREL, where I'm currently working, and the organization that sponsors my research in this area. I was also part of 2 groups at the University of Michigan, the Global CO2 Initiative, which works on CCU technologies, and the Center for Sustainable Systems, which focuses on improving sustainability of technology and engineering systems. I'd like to thank faculty member at UMich, Gregory Keolian, Shelley Miller, Fulka Sik, Dio, and Victor Lee, and my colleague at NREL, Dr. Joshua Shadley. So with that, I'd like to move on to the agenda of the talk. So these are the broad areas that I intend to focus on in today's talk. And a very brief introduction to what carbon capture and utilization is, how we can apply this method called Anticipatory LCA to address current limitations in LCA of CCU technologies. CCU in this talk, I'm going to use it pretty often in carbon capture and utilization. Then I'll just discuss briefly about the method of analysis. Then I'll focus on a specific case study, CCU concrete. So this is one of the 3 technology streams I'm going to be focusing on, along with CCU chemicals and CCU minerals. Then finally, the question, which CCU product, is it concrete, chemicals, or minerals, that produces the greatest climate benefit? So with that, I'd like to give you a brief introduction to carbon capture and utilization. So what exactly is carbon capture and utilization? If I have to summarize it, it's utilizing CO2 emissions, which is a waste of global concern now, and manufacturing commercially viable products like concrete, chemicals, or aggregate. So why is this important? We all know that we have a very short amount of time to deal with climate change and mitigate climate impact. And in this context, CCU is very important because it gives us an economically attractive pathway. So we are not just sequestering carbon dioxide in the ground, but we're actually using CO2 as a feedstock to produce commercially viable products. So in that way, it is pretty attractive. And as you can see, there's been a lot of interest, funding, and R&D efforts to develop CCU technologies. So it's been receiving increasing focus of late. As an indicator of this, there was a recent study that conducted an evaluation to understand what is the environmental and economic potential. If you look at the left figure, it shows you that there is a significant promise in utilizing CO2 by 2030. Significant quantities of CO2 can be utilized in producing various kinds of products. And equally important, there is economic potential too in terms of generating revenue, because we are making commercially valuable products from CO2. So it's not just an environmental project, but it's a project with pretty significant economic potential too. So this combination of economics and the environment make it very attractive, not just from a policy perspective, but from a commercial perspective too. There are a couple of firms that are operating CCU technologies at a commercial scale, but there are a very limited number. But that's a good indicator that yes, industry is interested in CCU as a way of increasing revenue and addressing climate change simultaneously. So now I'm going to just give you a brief overview of what anticipatory LCA is, and how it can address current limitations in existing LCAs of CCU. So this diagram over here represents the typical technology flow. We capture CO2 from the emissions, CO2 emissions from industrial processes. Then we use renewable electricity in combination with CO2 to produce a CCU product through CCU technology development. The reason why we need renewable electricity is in a couple of pathways, especially in pathways which produce chemicals, we need hydrogen to combine with CO2 to produce the end product, for example, like methanol. And obviously, we want to produce hydrogen through the renewable pathway and not through fossil fuels, because we want to reduce the footprint of hydrogen, which is used, carbon footprint of hydrogen that's used in the production of CCU chemicals. So this is the typical approach, systems approach towards CCU technology development. And if you looked at most of these studies, they make an implicit assumption that the utilization of CO2 produces a climate benefit, so CCU technology is good for the environment. But if you want to look at it more from a very robust, systematic perspective, from a life cycle perspective, we need to understand that we are developing a host of technology. So we need to have abilities to compare different potential emerging pathways to develop CCU technologies and rank them by climate benefits. So we're trying to understand which pathway is better in terms of implementing a CCU technology. Then we always have the issue of uncertainty, data uncertainty, because a host of these CCU technologies, a large majority of them are in the early stages of technology development, low TRL technology. So there's an issue of data uncertainty when trying to run a life cycle assessment to evaluate climate impacts. Then the third key point is, how do we incorporate sustainability in the early stages of technology development? How do we interact as LCA practitioners? How do we interact with technology developers and provide them with guidance as to what are the most effective R&D strategies that can further increase the climate benefits from CCU technologies? Then there are certain system aspects. As I told you, we are going to use renewable electricity in CCU technologies. So the question is it better off to use renewable electricity in other applications? For example, supplying renewable electricity to the grid, where it can offset or avoid more CO2 emissions rather than when used in CCU technology development. And also, how do we account for the functional units? For example, in certain pathways like concrete, when concrete is produced from carbon dioxide, material properties change. Whereas if a chemical is produced, that issue is not there, because methanol, for example, methanol produced through the conventional pathway or through CCU is going to be the same, but that's not the case in certain pathways like concrete. So how do we select functional units? So these are certain aspects that have not been robustly and systematically investigated from a broader perspective. So that's where I'm trying to apply this anticipatory LCA method for emerging technologies. So this is how I can visually represent what I'm trying to do in my research. So the key aspect is, now we're going to produce a lot of CCU technologies based using captured CO2. I'm going to conduct a stochastic assessment of the climate benefits produced from each of the CCU technology pathways, then compare them to understand which pathways, which CCU technologies produce a greater climate benefit and which of those pathways don't produce a climate benefit from a life cycle perspective. So when I'm running this assessment, I'm accounting for uncertainty in data because most of these technologies are in the early stages of technology development. So based on these findings, I can identify hotspots and LCA can help provide guidance to technology developers. So this happens in real time. So we're not waiting for a CCU technology to be commercialized and then trying to improve its environmental performance. There are a lot of technology lock-ins, commercial lock-ins that happen when technology reaches a commercial stage. So we're trying to address these sustainability challenges in the early stages of technology development. And I'm also accounting for system aspects like, can the renewable energy be put to better use, for example, on the grid? I call it the environmental opportunity cost of using renewable electricity in CCU technology development. So this is a broad framework, and it's depicted visually on the screen as to how I approach this problem of using anticipatory LCA to evaluate emerging CCU technologies. So with that, I'd like to dig a little deeper into the method of analysis. So as a part of that, first I'd like to start off with the system boundary. So as you can see, it's a pretty busy graphic over here, but I'd just like to discuss it briefly. So this is the way I look at a system boundary to conduct the LCA and evaluate the environmental performance of a CCU technology or a pathway. So I have CO2 that is being captured in a natural gas power plant over here. And that CO2 is captured through a post-combustion monoethanol amine system. And when we have the captured CO2, we can utilize it in producing either concrete, chemical, or minerals, the three broad categories that I've evaluated in my research. So the question is, where do we make use of the CO2 to produce the greatest benefits? Is it in concrete, chemicals, or minerals? So I'll be evaluating that using a metric called the climate return on investment, climate ROI metric, which I'm going to discuss later on. So as I've indicated over here, a couple of these pathways require hydrogen to produce chemicals. So we're going to make use of wind electricity to produce hydrogen through water electrolysis in certain pathways. It's also important to note that when we are running carbon capture in a combined cycle natural gas power plant, there's going to be an energy penalty because a lot of heat is used in capturing and releasing the CO2. So that heat would have ideally been used to produce electricity, but because we're running it for carbon capture, using it for carbon capture and utilization, there's a shortage of electricity. So to compensate for that, we're going to turn on an external power plant to make sure that there's no shortage of electricity. We compensate for that electricity. That's called the energy penalty that I've indicated with the term EP. So in effect, I'm accounting for all these system aspects, the production of concrete, chemicals, and minerals from a combined cycle natural gas power plant. I'm accounting for the production of hydrogen using wind electricity. So each of these processes has got a combined life cycle CO2 impact depicted by CCU CO2 over here. So I won't get into the details of each and every step, but a brief overview that suffices for now. And another important aspect that I have to tell you here is that the functional unit, when it's going to be concrete, we're going to use a compressive strength, which is measured in megapascals. The reason for that is when we use carbon dioxide to produce concrete, there's a change in compressive strength. So that's the reason we have to use a strength-based functional unit rather than just a mass-based functional unit. So that adds complexity to the analysis. Otherwise, for chemicals, we're going to use kgs of chemicals produced as a functional unit. For minerals, certain studies report the megapascal as a functional unit. Certain studies use kgs as a functional unit. So I'm going to use either kgs or megapascals when evaluating the climate impact of CCU minerals. So this is the CCU pathway that I've briefly described for now. So what I'm going to do is, obviously, we need to have a conventional pathway, because if CCU production is not happening, then we have the conventional production of a concrete, chemicals, or minerals. So in the conventional pathway, an equivalent pathway is there's no carbon capture in the natural gas power plant. wind electricity is going to be supplied to the grid directly. So that represents the environmental opportunity cost because that wind electricity can offset CO2 on the grid. And the three products are going to be produced through conventional means. So in order to gather data to conduct this comparative anticipatory life cycle assessment, I've gathered data from the inventory data from 99 data sets for concrete, 69 data sets from chemical CCU chemicals, and 26 data sets for minerals. So this is based on an extensive literature review to gather the data. And I've been running this LCA to determine the climate impact in SEMA Pro. So these are a set of brief methodological details that I seek to convey the presentation. So I broadly spoke about three categories, concrete, chemicals, and minerals. So in these three categories, I'm going to evaluate 4 concrete pathways over here, 13 chemical pathways over here, and 3 mineral pathways. So in sum total, I'm looking at 20 CCU products. I'm going to evaluate 20 CCU products and find out where is it best to use carbon dioxide in when comparing these pretty distinct, diverse set of pathways. I'm going to use this climate ROI metric, which I'm going to discuss in the future slides. So this is a brief overview of the methods that I've used when running this anticipatory LCA. So as I mentioned before, I'm going to talk about the net climate impact of concrete initially. And this is a case study that I'm going to use before I go on to the other pathways. So why have I focused on concrete as a part of carbon capture and utilization? The reason for that is concrete, as the study shows, contributes around 4 to 5% of the global CO2 emissions. And more importantly, it's one of the hard to decarbonize sector along with other major sectors like iron and steel. So the production of cement, which is part of concrete, it's a hard to decarbonize sector. So in this context, if we can make use of CO2 to produce cement itself, that will be beneficial for the environment and also help decarbonize the cement sector. So that's the reason I picked up this case study. So the way I'm going to analyze the results, I'm going to give you an indicative graphic over here. I'm going to use the system in the future slides. So I'm going to use this net CO2 benefit. That's the difference between the life cycle CO2 emissions from the conventional production of concrete minus the CCU pathway. As I'm accounting for uncertainty, the net CO2 benefit will be plotted as a distribution curve. And if it's going to be in the negative X direction, if it is negative, that means CCU concrete production produces a climate burden, because that means the CO2 footprint of CO2 is greater than the conventional production of concrete. So if the value of the net CO2 benefit is in the negative X direction, then it produces a climate burden. If it is in the positive X direction, it's going to produce a climate benefit. So then you see this percentage value at the bottom of the graph that indicates the likelihood of CC concrete to produce a climate benefit, because we are accounting for uncertainty in the analysis. Everything is depicted on a stochastic or a probabilistic basis. So because this distribution curve lies entirely in the negative X direction, there's a 0% likelihood of CCU concrete producing a climate benefit for this specific data set. So this is one of the 99 data sets. To make it more visually obvious, if this percentage value is greater than 50, then I'm indicating the background in green. If it's less than 50%, the background is in red. So in this case, it is in red because it is 0%. And red is bad for the environment, green is good for the environment. Green, there's a higher likelihood of CCU concrete to produce a climate benefit. So I'm going to extend this visual depiction to 99 data sets in my next slide. So I won't be getting into the 99 data sets here. I won't get into the details of it. There's no time for that. So broadly, the key findings from this is if you actually count the number of red graphs over here, so this is represents the state of art of CCU concrete production from different studies. In 58 out of the 99 data sets, there's a greater likelihood that CCU concrete produces a climate burden. And so what we have to understand is, because CCU concrete utilizes CO2, that does not mean it's going to produce a climate benefit, net climate benefit on a life cycle basis. So that's a key understanding at least based on the current state of the art, there's a higher likelihood that CCU concrete produces a climate burden. So the next step is, what is the reason for this? Why is it that CCU concrete currently tends to be more climate intensive than it should be? So for that, we conducted a sensitivity analysis. So this is how I'm going to represent the results of the sensitivity analysis. As you can see over here, we've analyzed 13 contributing processes, the processes that are part of CCU concrete production. So we've run a moment independent sensitivity analysis. So you get a delta value that indicates the sensitivity of the net climate benefit to each of these 13 processes. And the way we represent it is, we represent the delta values for each of the 13 processes. The greater the magnitude of the delta value, the more influence that specific process has on the net climate benefit. And if it is in the negative X direction, that means that specific process is resulting in CCU concrete to produce a climate burden. If it is in the positive X direction, that specific process is resulting in CCU concrete to produce a climate benefit. So using this system, you can see in this specific case study that the purple bar, that's the largest contributor because it has the highest delta value. Purple is the production of OPC. OPC is ordinary Portland cement. So OPC production is what is causing CCU concrete to produce a greater climate burden than conventional concrete. So this is the schematic and visual schematic I'm going to use. I'm extending this to the 99 data sets for concrete production. Again, this is a pretty busy graph. So the key findings, if you look at the key drivers, if you go through each of these graphs, there are 3 key parameters which occur repeatedly to determine whether CCU concrete is more climate burdens, produces a climate benefit or not. So the key drivers is the cement use, as I told you in the previous slide. You can see the purple bars pop up pretty often in these graphs over here. The second one is the orange graph, the use of supplementary cementitious materials. And the third one is the black bar, which is the energy used in curing of concrete with CCU. So this analysis actually helped us understand why CCU concrete is tending to be climate intensive. The reason for that is when we use CO2 in the curing of concrete, it tends to decrease the compressive strength of concrete. So what that means is that for the same amount of cement used in conventional concrete and in CCU concrete, we tend to get less strength in CCU concrete. So this means that we need, indirectly, we need to use more cement to generate concrete with the same strength in CCU when compared to conventional concrete. So as a result, if you're going to increase cement use in concrete production in the CCU pathway, we know cement is going to be extremely carbon intensive. So what that means from a life cycle perspective is that you are the carbon emissions from increased cement use in CCU concrete outweighs the climate benefits from utilizing CO2 in CCU concrete. So this is an important finding. So what we need to do then is we need to ensure, we have to work with concrete and material scientists to understand what is driving the reduction in compressive strength when CO2 is used. And we need to ensure that when we're using CO2 to produce CCU concrete, we need to maintain the compressive strength when compared to conventional concrete, or even better, increase the compressive strength. So that will ensure that CCU concrete is going to be more beneficial from a climate perspective than conventional concrete. So these were a set of key findings based on anticipatory LCA for CCU concrete. So now I'm going to take a step back and focus on the other pathways too. How do we compare carbon dioxide utilization for concrete versus chemicals and minerals? Just to refresh your memory, this was the schematic that I showed you previously, and I told you that I'll be talking about the climate ROI metric, which is going to help us decide where we want to invest CO2 and where do we want to utilize CO2 in producing concrete, chemicals, or minerals. So this is just to refresh your memory. So I talked about the climate return on investment metric. So broadly, the climate ROI metric helps compare the climate benefit across different CCU products. It accounts for the different diverse functional units. As I told you, chemicals can have a kg-based function unit, whereas concrete has megapascal compressive strength-based function unit. So it helps us overcome this challenge of accounting for different kinds of functional units, and thereby it also accounts for the change in material property in certain pathways, for example, in concrete. So this is the formula I use, the relationship I use to determine climate ROI. Climate ROI is a unitless metric. So broadly, I won't get into the details of each term. The numerator helps us determine what is the CO2 avoided on a life cycle basis per functional unit of the CCU product that is produced. The denominator tells you how much of CO2 is utilized per functional unit of the CCU product. So in effect, what you're trying to determine here is what is the climate benefit per kg of CO2 utilized in producing a CCU product. So what this means is that the more positive climate ROI is, it's greater than zero, and the more positive it is, that specific CCU product generates a greater climate benefit than a CCU product or a pathway with a lower climate ROI. So you ideally want this climate ROI to be as high as possible in the positive direction. And if it tends to be very negative, then that pathway, CCU pathway, is not really producing a climate benefit, rather it's producing a climate burden. As I'll be showing you in the results, I'm going to determine climate ROI on a stochastic basis. So there's going to be a distribution. And the implicit assumption here is that the production of a CCU product is going to offset a conventional product which is produced in the conventional route. So this is the brief overview of the climate ROI metric. It's a unitless metric, to re-emphasize, and we want it to be as positive as possible. So with that, I'd like to move on to the next couple of slides where I'm going to show you the results. So this is again an illustrative case study. It will help you interpret the results in the future slides easily. So as I told you, the climate ROI is unitless, and it can be either greater than zero when it's producing a climate benefit. If it's less than zero, it's producing a climate burden. Here I've showed you two specific pathways. I told you I'm discussing 20 pathways. So I picked out two pathways, P2, which is concrete production using CO2 mixing, and P11, which is the production of formic acid from captured carbon dioxide. So there are two key numbers here. For P2, it is 70%. So what this means is that out of 2000 runs, this distribution, we get this distribution from 2000 Monte Carlo runs, which determine the climate ROI of concrete when CO2 is used in the mixing of concrete. In 70% of those 2000 runs, climate ROI tended to be greater than zero. So it's producing a climate benefit. The corresponding value for formic acid is 96%. So in 96% of the 2000 runs, formic acid tended to have a positive climate ROI or produce a climate benefit. So you have to understand that I've run this for each individual pathway. So this is an absolute assessment. I'm not running a comparison. I'm running an absolute assessment. I'm evaluating the climate ROI for each of the individual 20 pathways. So I'm extending this analysis for the 20 pathways that I've shown you here on this graph. This graph is a very busy graph with a lot of distribution curves with uncertainty depicted. So this is a point of the graph to show that when we're evaluating the climate benefits of CCU, diverse CCU pathways, which are in the early stages of TRL, there's a significant degree of uncertainty. We don't need to go through each of these curves. As you've seen over here, there's a significant spread in the values, and there's certain values which are really negative in terms of the climate ROI, which is not good for the environment. There's certain pathways with a high level of positive climate ROI, which is good for the environment. So I've used 20 pathways. For certain pathways, I've calculated the values with and without the environmental opportunity cost. For example, if you don't, in this P17 pathway, if you don't consider the environmental opportunity cost of renewable energy use, then formic acid has a 31% likelihood of producing a climate benefit based on the climate ROI values. If we account for the environmental opportunity cost, then formic acid has an 8% likelihood. So accounting for the environmental opportunity cost is important because it gives you a true picture that the renewable electricity can be put to better use on the grid. So the key findings from this graph, there are 4 pathways, P8, carbon monoxide, P11, formic acid, P1 and P2, where we produce concrete through CO2 mixing. that tend to be beneficial, produce the greatest benefits individually. I'm not comparing them again. So these 4 pathways tend to produce the greatest climate benefits. And as I mentioned previously, with the example of formic acid, if we calculate the climate ROI without the environmental opportunity cost, it tends to inflate the climate benefits. But if we account for the environmental opportunity cost, we get a true measure that's saying that the climate benefits from a CCU pathway, which requires renewable electricity, is not really great because that renewable electricity can be used on the grid. So these are some of the key findings from this analysis when I conducted an absolute assessment of the climate benefit from each of the 20 CCU pathways. With that, I'd like to move on to shift the mode of assessment from an absolute mode to a comparative mode. What I showed you previously was an absolute mode where I quantified the likelihood of P2 and P11 pathways producing a climate benefit in 2000 Monte Carlo runs. So here I'm going to this heat map over here, I'm going to compare P2 and P11. So I'm going to conduct a pairwise comparison of the 2000 climate ROI values for P2 and P11 pathways. So you read this table horizontally. So this specific cell over here, which has 70%, it tells you that if you're going to conduct a pairwise comparison of the 2000 Monte Carlo runs, P2 has 70% likelihood as emerging as a winner. That is, in 70% of the 2000 Monte Carlo runs, P2 tends to have a higher climate ROI value, so it tends to be preferable from a climate perspective than P11. So that's why P2 is placed on the top row and P11 is placed on the bottom row. So what this means is that in this heat map table, which represents the results of the comparative assessment, the pathways that occur in the top rows, they tend to be preferable from a climate perspective than the pathways that occur in the lower rows of the heat map. So that's the way we interpret the results. Then I also have, by running a sensitivity analysis, we have identified the key climate ROI hotspot. What is the process that contributes the most to the climate ROI of P2 concrete? It happens to be the consumption of ordinary Portland cement, which I told you previously is the driver. And also for P11 formic acid, the climate ROI hotspot is the production of steam, the usage of steam in the process. So these are kind of like the R&D priorities. They can be used to guide technology development. So there's a lot happening in this figure. So these are the 2 pathways that I've shown you as an example. Now I'm going to extend this analysis to all the 20 pathways. Again, this is a pretty busy graph, so I won't be going through each of these pathways over here. Only thing you have to realize is as we go to the lower rows, the climate benefit tends to decrease. So the rows on the top tend to have a greater climate benefits. The pathways on the top rows tend to have produced a greater climate benefit. So if I have to summarize the findings tell you that these 4 pathways, which I discussed previously, they tend to produce the greatest climate benefit per kg of CO2 utilized on a relative basis. So if you ideally had an option to utilize CO2, it's better to utilize them in these 4 pathways to realize a greater climate benefit. Energy use is the key hotspot for the chemical pathways, and the consumption of cement, as I told you previously, and the usage of electricity in the CO2 curing process itself are the hotspots in the cement pathways. So this is a brief overview of the comparative assessment. So basically these 4 pathways are probably the best pathways to utilize CO2 in. Now I'm just going to give you a couple of brief scenario analysis. So the first one investigates the results. What happens when the environmental opportunity cost of renewable electricity is 0? Because we know that the grids are tending to become greener and greener. So renewable electricity on a green grid, probably we'd rather use it in carbon capture and utilization, because on the grid too, there's not much potential to offset CO2 when the grid becomes really green. So that's one scenario in which the environmental opportunity cost of using renewable electricity is 0 when the grid itself is green. The second one is we can use renewable electricity from captive plants. So the purpose of a power plant then is to only power the CCU operations. So there's no possibility of supplying that electricity to the grid. So therefore the opportunity cost is 0. or the use of curtailed electricity. The curtailed electricity is basically you're not supplying into the grid because it exceeds the grid capacity to transport or transmit renewable electricity. So in that case, that renewable electricity which is curtailed, you rather use it in CCU products. So in this scenario, what happens when the environmental opportunity cost is zero? The results are still the same. It still holds these four pathways tend to produce the greatest climate benefit per kg of CO2 utilized. So that was the key finding. If you're going to remove the environmental opportunity cost, the results still hold. These are the four most preferable pathways. The next scenario analysis that we conducted was what happens when we use zero carbon heat, because as I told you previously, in the chemical pathways, the hotspot tended to be electricity use and heat use. So when we ran the analysis with an ideal assumption that we're going to use waste heat, therefore zero carbon heat, what happens is the findings still hold these four pathways, which I told you previously, P8, P11, P1, and P2. Production of carbon monoxide, formic acid, and concrete through CO2 mixing. They tend to be the best pathways to utilize CO2 in. So with that, I'd like to summarize all that I've discussed with you today. So as I've showed you, Anticipatory LCA helps to address or identify issues of data uncertainty and account for them, more importantly, when conducting the LCA. It helps you compare different CCU products and guide technology development by identifying hotspots in the early stages of technology development. As I told you, there's a higher likelihood that concrete produced through CO2 curing will not generate a climate benefit. Again, this is based on the current assessment. Obviously, technology can improve, and we've provided ways in which it can be improved significantly. Then there are four pathways, CCU pathways, the production of carbon monoxide, formic acid, concrete through CO2 mixing that tend to generate the highest climate benefit among the 20 products that were analyzed. And for now, based on the current grid CO2 intensity, it's better to use renewable electricity on the grid rather than for the production of CCU products. And if you're interested in further details, I couldn't cover a lot of details because of the 30 to 35-minute timeline. I've linked the papers here which produced this research. Further details on this research that I presented can be obtained from these papers. If you can't find them, please do get in touch with me. I can provide you a copy of the papers. So thank you so much again for your time. So that's the close of my presentation, and I'd like to open it up for questions. Thank you again, EarthShift, and thank you each of the audience members for your time during this talk.
Thank you, Dwarak. I can't say that I understood everything, but I'm sure our audience did. I have the first person says, thanks, Dwarak. Do you consider impacts other than climate change?
Yes, that's a great question. For now, at least, we have not run the analysis for other impacts, other environmental impact categories, because we thought this in itself took a lot of time and space in terms of the paper, writing the paper, but definitely the analysis that I've shown you here can be extended to other environmental impact categories. Also, speaking of economic and TEAs, so we are also planning to run techno-economic assessment for a lot of these pathways. At NREL, they've already run some TEAs too for existing chemical pathways. And I'm currently working on ways in which we can integrate economic and environmental assessment results so that we can identify pathways that are most preferable, not just from a climate perspective, but from a more holistic environmental and economic perspective. So we're planning to use MCDA to integrate economic and environmental assessment.
Thank you. Do you find a relationship between the location where the data on the climate burden of the different technologies?
So for now, I mean, the potential ways in which the climate impact can be impacted by location is obviously one I told you is the grid location. So for example, if renewable energy that is used in CCU in products, if that happens to be in a very green grid, for example, Iceland or Vermont, which tend to have very green grids, then in that particular scenario, the opportunity cost of renewable energy use reduces. The other key impacts is what is the presence of the power plants or emitters of CO2, sources of CO2. They tend to be more clustered in certain regions where it's probably easier to scale the capture of CO2 also the existence of transportation facilities for CO2, like CO2 pipelines. So those are certain aspects in which geography will impact the results. So those are certain factors that I could think of now. Yes, that's my answer.
Okay, and there are people wondering if the study is published somewhere and if you could provide a link to it?
Yeah, so can you see the slide?
Yeah, maybe you could put it, Sam, could you put that in the chat, please? And then we'll move on to the next question. And there's another similar question. Will the related data sets be placed into the LCA data commons, lcacommons.gov?
I don't know about that. That I'll have to discuss with my team at NREL, my supervisor, Joshua Shadley. But one thing is we have provided extensive documentation in these 3 papers. The last paper, especially, which is currently in review in ESNT, and we hope to be published soon. The essay has got all the details, like how we use the data sets from CIMAPRO, what kind of data sets we used, what were the underlying assumptions, so on and so forth. So it is public from the paper perspective, but we haven't taken a call on whether to upload it in terms of probably open LCA or other platforms like the .gov platforms.
Okay.
We hope to do it in the future.
Okay. Is this climate opportunity cost metric being considered in the development of new policies for CCU technology deployment and selection?
I have not come across an extensive use of this environmental opportunity cost or equivalent metrics. In fact, there have been very few papers. One of these is where we use that to quantify climate opportunity cost of renewable energy use in methanol production, and there are a couple of other papers. But if you ask me, it's not really a very big concern for now, at least in CCU policy, because most of the papers I've seen, they assume that green hydrogen is available for free, which is not the case.
Okay. And someone is very interested in what exactly were the scenarios that were considered and how are the probabilities determined?
So are you referring to the scenario analysis? More details on the questions. So if you're referring to the scenario analysis, I've told you that the first one is we assume that the opportunity cost becomes 0 because of these 3 specific assumptions, and we run the analysis. The second one is we make an ideal assumption that waste heat is used in the production of CCU chemicals. So we are not assigned a probability for each of these scenarios. These are just more of an exploratory analysis in terms of the scenarios that were set up. So we're not assumed the probability of the scenario actually happening. It's more of an exploratory analysis.
Okay. And someone he says, you used already existing data sets in the analysis, yet if you were analyzing a process with no data sets or some key data sets were missing, how would this person proceed?
Yes, so that was, in fact, when we are shortlisting the data, when I was shortlisting the data to be included or excluded from the analysis, if the inventory data was not presented, unfortunately, we need a starting point. If the inventory data was not used or presented in the study in a transparent manner, we couldn't include it in the analysis. So obviously, with 0 data, it's not possible to run the LCA. So we use the best assumptions possible with inventory data, openly available studies when conducting this analysis. So in case the data is not publicly available and we want to run this analysis, we can work with the technology developers on a more confidential partnership kind of way rather than obtaining data sets from open studies.
Someone says, thank you for this amazing talk. I've got a lot of questions I'd like to discuss with you in detail, but let's start with your assumptions. What parameters and their ranges varied in your Monte Carlo analysis?
So one is definitely we use, for example, when determining the life cycle CO2 footprint of the material and energy inventory items that was obtained from the eco-environment data set through CIMAPRO. Then we also accounted for the variability, for example, in material properties. So for example, if you're going to use concrete, CCU concrete, if the strength varied from 20 megapascal per meter cube of concrete, 20 to 25 megapascal. The material properties, the variance in material properties were accounted for. The variance in the CO2 footprint of the material and energy inventory items, those were accounted for. So those are the two main contributors, which led to the uncertainty and the Monte Carlo assessment, the spread in the results. So the variance in the material properties and the variance in the CO2 footprint associated with the inventory items that were consumed in the production of CCU products.
And the same person asks what parameters and their ranges were varied in your MCA.
So, and the third category again is we also used variability in the grid factors because that relates to the environmental opportunity cost. So all of these three parameters are varied. One is the change in material properties, the variation in the material and energy inventory items that were consumed as part of the analysis, the variation in the uncertainty in the CO2 footprint of the material and energy inventory items that were consumed in CCU product production. And the fourth one was the variation in the grid CO2 intensities at a national level. So those are the four key parameters that are varied in the analysis.
Okay, and then someone asks, certainty is determined from the analysis of the data sets or comes from other sources? Is the uncertainty determined from the analysis of the data sets or comes from other sources?
From the data sets, as I told you. So it's the inventory items and the material properties, they were obtained from the data sets, which form the basis of the analysis.
Okay, and one more. Do you think comprehensive strength is a right metric for comparing concrete mixtures' environmental impacts?
I won't say it's the only metric because, as I told you, that's one of the key material properties. There are other material properties like durability that have not been studied as extensively as compressive strength. That happens to be the industry standard and the most. In fact, I would say that's not the proper metric. Most of the studies use a mass-based metric for concrete, which is not as useful as a material property. But besides compressive strength, there are other material properties like durability that can be investigated in the future. Unfortunately, we don't have enough data on durability in the studies in the 99 data sets to run a comprehensive analysis. So I would say we need to repeat this analysis for compressive strength for other material properties like durability.
Okay, actually, let me give one more question who says, did you account for the emissions associated with the post-combustion carbon capture technology? i.e. the production of the post-combustion carbon capture technology, for example, gas membranes, etc.?
Yes, I use, as I told you, it was an MEA system. We did account for the production of MEA. In fact, if you look at this, the production of MEA is process P7, so that was accounted for in the analysis. So the amount of CO2 emitted in producing the MEA system that is required for post-combustion capture of CO2 in the power plant, it was accounted for.
Okay. Well, I want to thank you, Dwarak, very much for this interesting talk. We have so many more questions that people can contact you privately for, but I just wanted to let people know that we do have this Anticipatory LCA class coming up on July 20th to 21st. We changed the dates. And we have an all-star team of Lisa Lauren, Valentina Prado, both from us, EarthShift Global, as well as Tom Steger and Tom Etheridge from Equilibrio. So please consider that. And additionally, we have the next webinar coming next month. We will have Timothy Scone from the DOE National Energy Technology Laboratory telling us about sustainable water management for decarbonizing fossil power generation. So thank you again, everybody, specifically to you, Dwarak, and I will end this webinar. Thanks.
Thank you. Thank you all.